So in Chapter 11, Section 8, we're going to be talking about power series. So the idea of a power series is we want to represent a function as the sum of monomials. And what I mean by that, in essence, what we're saying is, can we represent a function by writing it as an infinitely long polynomial? And we're going to find out that the answer is yes, comma, sometimes. And we're going to study when we can and can't do this and different types of power series and then some other types of series as well. So a power series then is a series that has the form, the sum, as n goes from 0 to infinity, of c sub n times x to the n. That is, it is a constant plus a linear term plus a quadratic term and so forth. We've actually seen something like this before. Back in Calc 1, we did linear approximations of a function. Well, a linear approximation would just be the first two terms of this series. And if you want to make your approximation better, you could keep adding more and more terms to get our desired accuracy. So the c sub n's are called the coefficients of the series. And so C0 is different than C1 is different than C2 and so forth. So let's take a look at our first example. So example 1, the geometric series with common ratio, it's not a ration, that's not even a word, common ratio x is given by 1 plus x squared plus x cubed, because this would just be a times r to the n minus 1. So our a sub n's would be a times r to the n minus 1, where our a is 1. So we would just have r to the n minus 1. And, or in this case, it would just be r, because we've re-indexed our series. And so if we plug into the 0 power, we get 1. X squared, x, and so forth, or x to the n. I used r, but in this case we really meant x, because we said r was x. So x to the n, and that would be convergent as long as our common ratio is less than 1. So that converges when the absolute value of x is less than 1, and it converges to the sum of our geometric series, which is 1 over 1 minus r, because our a is 1. So we had a1 over 1 minus r. In this case, that would be 1 over 1 minus x. And so that would converge to the sum of this series. So if we look at our graph here, and we have our black graph is the graph of 1 over 1 minus x. And then if we look at the partial sums, we see the more terms that we add to this series, the closer and closer we get to that approximation. So this gives us then that our function f of x, which equals 1 over 1 minus x, is equal to the infinite sum as n goes from 0 to infinity of x to the n. That is this series. So how could we show that this series does indeed converge as we were told here? Well, we could use the ratio test. So the ratio test, we would identify our a sub n as x to the n, and the ratio test is the limit as n goes to infinity of the nth root of a sub n, which would be the limit as n goes to infinity of the nth root of x to the n. Well, the nth root and the nth power reduce out, and that gives us the absolute value of x. And from the ratio test, we know that a series, or the root test, we know that a series converges if the limit converges absolutely if the limit is less than 1. So that is, this will converge if the absolute value of x is less than 1, which is what was claimed up here. So that is as a result of this, and I said ratio test. I really meant root test. All right, so let's take a look at our next example. So for what values of x does the series, the sum as n goes from 0 to infinity of n factorial times x to the n? So oftentimes when we have factorials, the ratio test is a good idea. So let's try the ratio test. And the ratio test is the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n. And we need this to be less than 1. So we need the values of x where this is less than 1. So let's go ahead and calculate our limit. So we take the limit as n goes to infinity of our absolute value. So a sub n plus 1 is going to be n plus 1 factorial times x to the n plus 1 divided by n factorial x to the n. So we do some algebra and expand our factorial. So that gives us n plus 1 times n factorial x to the n times x all over n factorial x to the n. N factorials reduce out, and the x to the n's reduce out. And we're left with the limit as n goes to infinity of n plus 1 times the absolute value of x. And we want this to be less than 1, but we have a little bit of a problem. As n goes to infinity, n plus 1, this is going to go to infinity. The only way that this thing is not going to be infinity is if x is 0. Is not plus or minus infinity is if x equals 0. And if x was 0, then our original series would have been just 0 plus 0 plus 0 plus 0 plus 0. So this only converges if x equals 0. So in our first example, we had it converge if the absolute value of x was less than 1. Here it converged if, and only if, x were equal to 0. So the next one is for you guys. So you try number 1. So we want to determine for what values of x does the series 2x to the n over 5 to the n converge. Alright, so to determine what values of x this converges for, we identify our a sub n, and our a sub n is going to be 2x to the n all over 5 to the n. And if we use the root test, and if you use the ratio test, you'll get the same thing. We need to know, well, when is the limit as n goes to infinity of the absolute value of the nth root of the a sub n's, when is this less than 1? Well, this is what we want. So we calculate our limit. We have the limit as n goes to infinity of the nth root of 2x to the n all over 5 to the n in absolute value. And here, the nth roots cancel the nth powers. And in fact, there's no n's left. So this is equal to the absolute value of 2x over 5. And this needs to be less than 1. So we're going to solve for x. So to solve our absolute value inequality, we have -1 is less than 2x over 5 is less than 1. And then we need to isolate x. So if we multiply each part of this by 5, that gives us -5 is less than 2x is less than 5. We divide by 2, divide by 2, divide by 2. And we get -5/2 is less than x is less than +5/2. So then our series is going to converge for the x values between -5/2 and +5/2. So it's going to converge here. All right, so let's take a look at our next one. So we want to know, once again, for what values of x does this converge. So this time we're going to use our ratio test. And once again, we want the following. The limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, we want this to be less than 1. Our a sub n in this case is going to be x plus 2 to the n all over n times 3 to the n. So we start writing this out. We take our limit as n goes to infinity. A sub n plus 1 is going to be x plus 2 to the n plus 1 all over n plus 1 times 3 to the n plus 1 divided by a sub n, which is just x plus 2 to the n all over n times 3 to the n. So we need to simplify this up a bit. So we divide by the reciprocal of the denominator, and that's going to give us x plus 2 to the n plus 1 over n plus 1 times 3 to the n plus 1 times n times 3 to the n all over x plus 2 to the n. So we need to keep simplifying this. So we're going to use some of our properties of exponents. That if I have x to the a times x to the b, that's x to the a plus b. And we're going to use this property backwards because we have an n plus 1 here. So we can rewrite this as the limit as n goes to infinity of x plus 2 to the n times x plus 2 all over n plus 1 times 3 to the n times 3, so we use that property again, times n times 3 to the n all over x plus 2 to the n. After doing that, we get to cancel out some things, so our x plus 2's to the n reduce out, and our 3 to the n's reduce out. Our limit here, we'll notice, only depends on x. So we can actually pull that out of our limit. So we have the absolute value of x plus 2 times the limit as n goes to infinity of, we pulled this guy out in front of our limit, and then we have a constant 3 in the bottom. It can get pulled out in front. And our limit only depends on n, so that leaves us with n over n plus 1. So now when we evaluate this limit, we have infinity over infinity, which you could use L'Hopital's rule if you wanted to, or we could just do some algebra and reduce this to 1 over 1 plus 1 over n. And if that's the case, as n goes to infinity, this goes to 0. So that limit is going to be 1. So we get the absolute value of x plus 2 over 3 times 1. And we want this to be less than 1. So if we have the absolute value of x plus 2 over 3 is less than 1 in absolute value, this is the same as negative 1 is less than the absolute value of x plus 2. We're dropping the absolute values now because we're setting up the 3-part inequality over 3 is less than 1. And we multiply everything by 3 to reduce that out, and we get negative 3 is less than x plus 2 is less than 3. We minus 2, minus 2, minus 2, and negative 5 is less than x is less than 1. So our series converges when x is between negative 5 and negative 1. Something we haven't addressed so far is we must check the endpoints separately. And why is it that we have to do that? Well, if we go back to our sheet, what happens when either the ratio test or the root test, if the limit equals 1, we'll notice that that's choice 3 on this. It says that the test fails, so we have to use a different test. So that's why we're always doing when it's less than 1. When it equals 1, the series may converge or it may diverge. We don't know. So we plug in the x values at the endpoint, so we need to check when x is equal to negative 5. So if we put x equals negative 5 back into this series, we're going to have the sum as n goes from 0 to infinity of negative 5 plus 2 to the n all over n 3 to the n. So then this simplifies to the sum as n goes from 0 to infinity of negative 3 to the n all over n 3 to the n. Well, this is going to reduce to, we can write that as negative 1 to the n times 3 to the n. And if we do that, the 3 to the n's are going to reduce out. So we get the series as n goes from 0 to infinity of -1 to the n over n. And this is the alternating harmonic series. So this converges by the alternating series test. Or the fact that it's the alternating harmonic. So it's going to converge when x equals -5, and now we need to check when x equals 1, which is the other endpoint. So if we plug x equals 1 in, that's going to be the sum as n goes from 0 to infinity of 1 plus 2 to the n all over n 3 to the n, which is going to be the sum as n goes from 0 to infinity of 3 to the n over n 3 to the n. The 3 to the n's reduce out, and we get the sum as n goes from 0 to infinity of 1 over n. And this diverges. So this is the harmonic series, or p-test, p equals 1 diverges. So if we look at our sheet here, we go up to our p-series. So a series of this form, n to the p, converges if p was bigger than 1 and diverges if p is less than or equal to 1. And in our case, our p would be 1 exactly. So our series would diverge. So it converges when x equals -5, and it diverges when x equals to 1. So the power series converges on -5 to 1, including -5, but not including +1. All right. The next one is once again for you guys. So we want to determine for what values of x does this series converge. All right, so if we use the ratio test, we're going to take the limit as n goes to infinity of the absolute value of x minus 6 to the n plus 1 all over 2 times n plus 1 factorial all over x minus 6 to the n all over 2n factorial. So we multiply by the reciprocal of the denominator, and that gives us x minus 6. I'm going to split this up times x minus 6 to the n times x minus 6 over 2n plus 2 factorial times 2n factorial all over x minus 6 to the n. So our first bits cancel out, and we can factor out our x minus 6, but then we need to expand our factorial. So we have the limit as n goes to infinity of 2n factorial over, and 2n plus 2 factorial is 2n plus 2 times 2n plus 1 times 2n factorial. So then finally those reduce out, and we're left with this. So our limit then, as n goes to infinity, this goes to infinity and this goes to infinity. So we have a constant divided by infinity equals 0. So x minus 6 times 0 equals 0. So 0 is less than 1, so by the ratio test, the series converges for all x. That is from negative infinity to infinity. Alright, so we're actually going to just jump over the next example. It's just more of the same of what we've been doing. It's just called the Bessel function, but it's pretty much exactly like the example you guys just did. So let's take a look at our next example, because before it we have some definitions. So we've been dancing around some of these ideas a little bit. So let's formally go ahead and define everything. So theorem, for a power series n equals 0 to infinity of Cn times x minus a to the n, there are only three possibilities. And this is what we've seen in some of our examples. The series only converges when x equals a, so it converges only at its center. Or as we just saw in the previous U-try that you did, the series converges for all x. Or the third possibility is there's a positive number r such that the series converges if x minus a is less than r and diverges if it is x minus a in absolute value is greater than r. The number r is called the radius of convergence of the power series. By convention, for case 1, r equals 0, and in case 2, r equals infinity. So if it converges only at its center, we say the radius is 0. And if it converges for all real numbers, then we say that the radius of convergence is infinity. The interval of convergence is the interval that consists of all values of x for which the series converges. When x is an endpoint of the interval, anything can happen. The series might converge, diverge, or be different at each endpoint. So we've kind of seen some examples of all of these, but this is our theorem that ties all of those things together. So let's put all of them together in the context of this problem. So find the radius of convergence and the interval of convergence for the series n equals 0 to infinity of negative 3 to the n x to the n over the square root of n plus 1. So we need to determine if this converges or diverges. So let's use the ratio test. So we're going to take the limit as n goes to infinity of negative 3 to the n plus 1 x to the n plus 1 all over the square root of n plus 1 all over negative 3 to the n x to the n all over the square root of n plus 1. So once again, expanding and multiplying by the reciprocal, we have negative 3 to the n times negative 3, x to the n times x all over the square root of n plus 2 times the reciprocal, the square root of n plus 1 over negative 3 to the n x to the n. So a whole bunch of stuff reduces out, our x to the n and our x to the n, and this leaves us with the absolute value of negative 3 in x, so we get 3 times the absolute value of x times the limit as n goes to infinity of the square root of n plus 1 all over the square root of n plus 2. So if we factor our GCF of the square root of n out of each of those, and we take the limit as n goes to infinity, that gives us the square root of n times the square root of 1 plus 1 over n, and the square root of n times the square root of 1 plus 2 over n. And those reduce out, and as n goes to infinity, each of these go to 0, so that limit equals to 1. So we get 3 times the absolute value of x times 1, and we need this to be less than or equal to 1 for this to converge. So now we need to solve this inequality. So we divide by 3, and we have the absolute value of x is less than 1/3. So writing that as a 3-part inequality, we get negative 1/3 is less than x is less than positive 1/3. So this right here is our radius of convergence. So our radius of convergence is 1/3. And now we need to check our endpoints. So we need to check the endpoints. So if we check x equals negative 1/3, and we put that back into our original series, we're going to have the sum as n goes from 0 to infinity of negative 3 to the n times negative 1/3 to the n all divided by the square root of n plus 1. So if we simplify that up, negative 3 to the n times 1/3 to the n, a negative times a negative is positive. 3 times 1/3 is 1. We get 1 to the n, but 1 raised to any power is just 1. So we get the sum as n goes from 0 to infinity of 1 over the square root of n plus 1. So now we need to determine if this converges or diverges. So this is going to be of order n to the 1/2, because we have a constant 1 in the top and then the square root of n in the bottom, so n to the 1/2. So we will try limit comparison with 1 over n to the 1/2. And this is a divergent p-series. With p equal to 1/2. So if we go to our sheet here, we're doing our limit comparison test, which is this guy. So it says if the ANs and the BNs are both greater than 0, and the limit as n goes to infinity of AN over BN equals C, then either both series converge or both series diverge. So we're comparing using limit comparison with a divergent p-series. So if the limit as n goes to infinity of the ANs, which is 1 over the square root of n plus 1, over 1 over n to the 1/2, is bigger than 0, then both series diverge. So once again, we're going to multiply by the reciprocal. So we have the square root of n plus 1. I'm going to write this as the square root of n over 1. And if we factor a square root of n out of each of these, we're going to have the square root of n, square root of n. In the top, that leaves behind a 1, and in the bottom, that leaves behind a 1 over 1, the square root of 1 plus 1 over n. So as n goes to infinity, that goes to 0. Those reduce out, so we get 1 over 1, which equals 1. So by limit comparison, the series diverges. At x equals negative 1/3. So just to kind of recap, we checked our endpoint, we plugged in our x equals negative 1/3. That reduced to the series 1 over the square root of n plus 1, which we did limit comparison with 1 over the square root of n, or n to the 1/2, which is a divergent p-series. So by the limit comparison test, if we get a positive number for the limit, then both series either converge or diverge. So since we compared with a divergent p-series, the original series must have also diverged. All right, so that was one endpoint, and now we need to check the other endpoint. So we need to check x equals positive 1/3 this time. So if we do that, we're going to get the sum as n goes from 0 to infinity of negative 3 to the n times positive 1/3 to the n all over the square root of n plus 1. And when we simplify this, negative 3 to the n times 1/3 to the n gives us negative 1 to the n all over the square root of n plus 1. So then our a sub n is a negative 1 to the n all over the square root of n plus 1. So this is an alternating series. So by the alternating series test, we're going to get convergence. So the alternating series test states the following. By the alternating series test, so we see that it alternates, so we have this, and it's decreasing every time n increases. We're going to have that a to the n plus 1 is less than a to the n, because that's 1 over n plus 2 is less than 1 over n plus 1. Because if you make the denominator bigger, you make the fraction smaller. So this, and the limit as n goes to infinity of negative 1 to the n over the square root of n plus 1, a constant divided by infinity does equal 0. So the series converges by the alternating series test. So it diverged at negative 1/3 and it converged at positive 1/3. So our interval of convergence is this. So our radius of convergence was 1/3, and our interval of convergence is the interval from negative 1/3 to positive 1/3, not including negative 1/3, but including positive 1/3. So, to the very last one for today. So you try number 3 is the very last problem. So this one's for you guys. We want to find both the radius and the interval of convergence of this series. Once again, to test for convergence, we're going to use the ratio test. So take the limit as n goes to infinity of the a sub n plus 1, so n plus 1 times x plus 2 to the n plus 1 all over 3 to the n plus 1 plus 1, so that's going to be n plus 2, all over n times x plus 2 to the n all over 3 to the n plus 1. So multiplying by the reciprocal of the denominator again and separating, we get n plus 1 x plus 2 to the n times x plus 2 all over, and I'll write this as 3 to the n plus 1 times 3 times 3 to the n plus 1 over n times x plus 2 to the n. And as has happened with pretty much all of them, we get some things that reduce out as always. We pull out our absolute value of x plus 2 this time, and then we have the limit as n goes to infinity of n plus 1. We pull the 3 out of the denominator over n, and the limit as n goes to infinity of n plus 1 over n is going to be 1. So we get x plus 1, or x plus 2 in absolute value over 3 has to be less than 1. So writing that out, we have negative 1 is less than x plus 2 over 3 is less than 1. Clear our fractions by multiplying by 3. So negative 3 is less than x plus 2 is less than 3. Minus 2, minus 2, minus 2. Negative 5 is less than x is less than 1. So it's worth noting that at this point we have this right here is going to be our radius of convergence. It's 3, because if you take the distance from negative 5 to positive 1, the center is going to be here. This would be our radius, is 3 and 3. So the radius is always going to be half the distance between the endpoints of our convergence. So this converges for x values between negative 5 and 1, and they're 6 units apart, so the radius would have to be 3. And then if we check each of our endpoints, so if we check x equals negative 5, that gives us the series as n goes from 0 to infinity. And if I put negative 5 in, that's going to be negative 5 plus 2 is negative 3. So we get n negative 3 to the n all over 3 to the n plus 1. Well, separating that out, we're going to get n times negative 1 to the n times 3 to the n all over 3 to the n times 3. And our 3 to the n's reduce out, and we would get, pulling our 3 out in front, the sum as n goes from 0 to infinity of negative 1 to the n times n. And this is going to diverge by the test for divergence. Because the limit as n goes to infinity of our a sub n does not exist. So if we look at the test for divergence, it says if the limit as n goes to infinity of the a sub n's isn't 0, then the series diverges. So that just diverges by the test for divergence. And if we do x equals positive 1, we're going to get a very similar result. But this time, if we have x plus 2, 1 plus 2 gives us 3. So we get n, 3 to the n, all over 3 to the n plus 1. Well, this is going to equal 1/3 again. The sum as n goes from 0 to infinity of just n, because the 3 n's reduce out and we have 1/3 left over. And this is also going to diverge by the test for divergence, because the limit as n goes to infinity of n equals infinity. So also doesn't. So this series, the interval of convergence, is -5 to 1, and it doesn't converge at either